Good afternoon, all. I am Fernando Pereira, and it's my pleasure to talk about our work, the essence of the Flyweight Design Pattern, which I did together with Caio Raposo at the Federal University of Minas Gerais in Brazil. And by the way, it's pretty rainy down here in Brazil, so let's hope the rain will not be too noisy. Anyway, this paper is a homage to Jens Palsberg on the occasion of his 6th birthday. About 26 years ago, Jens was working on a similar paper about the essence of the visitor design pattern. Jens was teaching compilers, and he was a big fan of using visitors as a core technique to implement systems that process programming languages. Visitors are a way to decouple the representation of objects from the operations that these objects implement. It makes it easy to add new operations to a collection of objects without having to change the implementation of the objects. For instance, we can have a visitor eval, which evaluates objects representing programming language constructs, just like we could have a visitor print, which prints them, or a visitor optimize, which optimizes the representation, and so on and so forth. What's interesting is that the visitor pattern is pretty much native in functional programming languages. In functional programming, we add new operations to existing types all the time, and there is no need to change the types. We can think about each visit method as a pattern matching case. So, an interesting exercise is this. Can we think about other design patterns that could be implemented natively in other programming languages? Indeed, there are many. For instance, the template method and the strategy patterns are natively supported in languages that feature high-order functions. In this work, we shall look into the Flyweight Design Pattern, which is a way to minimize memory usage by sharing common data across multiple objects. The pattern could be implemented natively in an object-oriented language if it supported the memoization of object constructors. And so we want to implement this kind of memoization of constructors, but we want to do it safely. Memoization is an optimization that we use to avoid recomputing functions if they were already called. In Python, we can memoize functions with annotations such as cache, which is available in Python 3. But in this work, we shall be working onto another programming language. It's called Hush. I will talk more about it, but whenever showing examples, I will try to show examples in Python and in Hush, as Python is more well-known. So in Hush, we use an annotation called Mimo to indicate that a function is memoized. That's similar to the cache annotation in Python. Notice that Mimo is not semantically equivalent to Python's cache. Mimo is implemented in Hush's runtime. It's more efficient than Python's cache annotation, which is implemented as a Python library and does not change the runtime of the language. So our implementation of memoization is likely to outperform Python's, even though Hush is less efficient than Python in general. Now let me explain what I mean by safe memoization of mutable data. If we memoize the constructor of objects, we might create unintentional aliases that would be unsafe. I will show with this example in Python that represents 2D points. Let's create two memoized objects. We can create memoized objects by caching the class itself. So now we have that P0 and P1 are points to the same memory region as the point 11 is memoized. So what happens if I modify P1? This modification will also have an effect into P0 as these objects are aliases. And by modifying P1, we unintentionally modify P0 too. That's an unsafe modification due to a fake alias. Soon I will show how we avoid these problems. Before, I shall talk about Hush. Hush is a programming language that was developed by Gabriel Bastos, who was a student at the Federal University of Minas Gerais. Hush is implemented in Rust. It's a shell scripting language, so in purpose, it would be similar to Bash or tcuzzy. But synthetically, it's more similar to Lua, for instance. It is strongly typed, meaning that Hush programs meet progress and preservation. Hash is dynamically typed, a bit like Lua, Python, Bash, and such. It also has a garbage collector that's implemented in Rush. Indeed, Hash is fully implemented in Rust. The garbage collector is implemented in Rust. And it has first-class functions. This last feature will play a role in this presentation. Anyway, Hash is relatively popular. It has many users, some contributors, and you will see that it has some stars on GitHub. If you have the time, take a look at it. Here's a function in Hash. This function creates objects. Hash does not have classes. Objects are created as closures. A class is pretty much a function that returns a dictionary that contains state and behavior. That's the syntax for dictionaries, an object, a dictionary that's created explicitly, without any special syntax. In this example, our object contains an attribute, start, which is bound to n, which is the argument of the function that creates objects. And it contains two methods, which are simply functions bound to keys in the dictionary. Now let me do a small detour to explain what's the Flyweight Design Pattern. Again, this is a way to share data among objects. To demonstrate how that works, consider this example. Now in Python, I have students who are enrolled in courses. Each student has an ID and a name. A course is a set of students, meaning that we can add students to courses. And each ID is uniquely associated with a single student. So we use a central registry class to create students, pretty much like a factory. Before creating a student, we check if its ID was already seen. In this case, we return the object that's associated with that ID. Otherwise, if the ID has not been seen yet, we create a new object and store in the table, and then return the object. Here, on the right, we have the equivalent program written in Hash. We are memorizing the function that creates objects, so these two programs, the one in Python and the one in Hash, are equivalent, more or less. So now let me explain how we implement safe memorization. Basically, we want to ensure that we remove from the memorization table any object that's modified. For that, we use shared pointers. Let me illustrate how we do it using this program here, which creates memorized points. Without shared pointers, we would have the two pointers pointing to the same memory location, what would lead to an intentional alias. Instead, we shall access memorized objects via shared points. So there will be one level of interaction to access memorized objects, but no memorized object will be accessed as before. In this example, an alias of P0 will point to the same shared pointer. That's like P2 in this example. So all these objects in the end refer to the same memory location, which is memorized. But only P0 and P2 are aliases, as they point to the same shared pointer. P1, in contrast, is a pointer to a different shared pointer. If we modify P1, for instance, then what happens is that we remove the object pointed to by P1's shared pointer from the memorization table. This is what is commonly called the copy-on-write semantics. In this way, any new object is created on the memorization table and remains there as long as it's not modified. For instance, if we create a new object P3, then it will be stored in the memorization table. The semantics meets a number of properties which we discuss in the paper. We have actually formalized these properties using the alloy specification language. So any modification of a memorized object will cause the creation of a copy of this object. This new copy is not stored in the memorization table. The object itself, its representation in memory, remains memorized. The modified object, the data that's stored outside the memorization table. Notice that the modified object is still accessed through the same shared pointer. In other words, we don't have to update references, only shared pointers. This is all implemented in Hash's runtime engine. We have a version of Hash with Flyweight that's publicly available. It's pretty efficient. We have a number of experiments that show that in practice there is no runtime cost implementing safe memorization. I will show some experiments. To this end, we shall go over a number of research questions. In this work that motivated this paper, which is a master dissertation, we explore 4 research questions. The first is is there to show that memorization in Hush is efficient. The second question, which is the main result, shows that safe memorization is as efficient as unsafe memorization. A third research question, which I will not show in this presentation, analyzes the impact of the hashing strategy on the implementation of memorization. And then finally, the fourth research question, which also I don't show in this presentation, analyzes the interplay between memorization and garbage collection. So let me start by showing that memorization in Hush is very efficient. I mean, it's as efficient as it gets in a programming language where memorization is correctly implemented. I will show memorization of pure functions first, just so because memorization of objects, due to the nature of the benchmarks, does not really show the super nice numbers that we normally see in memorization. We have a repository with several benchmarks written in Hush. In this repository, we have 7 pure functions. These are functions that are typically memorized in other functional programming languages. For instance, here's the implementation of the Fibonacci sequence. This is the common exponential implementation. So I will compare the running time of the memorized and non-memorized function. In this case, we shall be counting from 1 to 40 all the Fibonacci numbers. And as expected, whereas the original implementation of Fibonacci is exponential, the memorized version is linear on n. So that's the expected behavior of memorization. Now let's take a look into some benchmarks that involve mutable objects. Again, the benchmarks are stored in our repository of Hush programs. We have 6 benchmarks that do memorization of mutable objects. And we have fiddled with 5 different implementations of memorization. Well, the first implementation does not really do any memorization. That's the original version of Hush. Then we have an implementation of unsafe memorization, just like the Python example that I showed in the beginning of this presentation. Then we have also an implementation of memorization with a guard to trigger an exception if we try to modify a memorized object. So this implementation actually stops the program if we try to modify memorized data. And then we have an implementation of shared points as a library outside the Hush runtime. This implementation is safe and does not require us modifying the implementation of the programming language. But as we'll see, it's not very efficient. And then we have the version of safe memorization with shared pointers implemented in the Hush runtime. That's our implementation of choice. So let me start with a simple benchmark. It represents polygons as a list of points. So creating an object, simply passing a sequence of 2D points to it. Then let's see how the different implementations of memorization fare when we vary the number of objects. I shall be showing running time on the y-axis. Here they are, our results. The implementation of memorization as a library is kind of inefficient. But the nice thing is that there is very little difference between the other implementations of memorization. In other words, safe memorization does not really impact much of the program's performance. Notice that this observation does not change as we see more or less collisions in the memorization table. In this particular example, memorization does not improve performance over the original version of Hush. The thing is that we are memorizing a very cheap constructor. It does not really do any computation other than storing points within a list. Let's then use these polygons to build more complex figures. In this case, we shall have objects that are figures made of polygons. The constructor arranges these polygons into complex figures. Again, we shall see how memorization does in terms of running time once we vary the number of objects. In this example, the constructor is more expensive and it pays off to memorize it. As you see, the original version of Hush without memorization is about 20% slower. And all the memorized versions of Hush do more or less the same. This independent of the rate of collisions among memorized objects. The bottom line is that there is not really a performance penalty to pay to implement safe memorization compared to the implementation of unsafe memorization. Okay, let me bring some final remarks. This paper brings a new technique to memorize functions. We are focusing on the correct memorization of mutable data. Our version of Hush is publicly available on the repository. And there are a few different lines of research that we believe could set off from this paper. For instance, implementing garbage collection when we have memoized objects is an interesting challenge. We have an implementation, but yet something that we consider ideal. Then there is also the cost of hashing. Memorization involves computing deep hashes, meaning hashes of graphs of objects. And I wonder if it's possible to cache some of these hashes. And then there is all this question of when it's worth to memorize data. Perhaps it's possible to implement automatic memorization whenever some analysis deems it profitable. Anyway, I'd like to finish saying that this work came from the master dissertation of Caio Raposo. Caio came from the north of Brazil to Belo Horizonte, the city where I work. I believe he did a good job, and I would like to thank him for that. And I close the presentation thanking CAPS as well, which is a research agency under the Brazilian Ministry of Education. CAPS sponsored Caio's scholarship and made this project possible. So thank you very much for your time.